Alright folks, here we are with question 24 on the 2004 Fermat paper. Thank you for joining me. The polynomial f of x satisfies the equation f of x minus f of x minus 2, can't speak today for some reason, is equal to 2x minus 1 squared for all x. If p and q are the coefficients of x squared and x respectively in f of x, then p plus q is equal to... What are we to do? Okay, so we don't quite know what the polynomial f of x looks like. I'm gonna bet that it's a cubic, just because its difference is quadratic, although should I go based on that assumption? Surely the way the question is phrased, if I can find a polynomial that satisfies this, it's got to work out. And that can sometimes help us cheat, because I have sort of the suspicion f should be cubic. I don't have the wherewithal to necessarily prove that right now. I have the suspicion it should be cubic, and if I can find a cubic that satisfies the only condition that makes f what it is in the question, then surely that should be fine, and I can just pick off the p and the q. So that's a bit of an exploit you can do, is sort of just find a thing that satisfies all the conditions that define the thing they're talking about. Because it might be that there's more than one f of x that does this, but that there's some fancy math proof that we don't need to do, it's not a written contest, but there might be some fancy math proof that shows us what p plus q should be. So if you can say, well, a cubic should work, here's this cubic, it does work, you don't have to know any of that math theory, you don't have to work in the abstract, you can work with a very real polynomial. But is there another way to do this? We ultimately want p plus q. Are there certain values of x I could plug in that might make my life a little easier? For example, if I plugged in, say, x equals 2, because what I'm thinking is this. Let's just copy our equation here. F of x minus f of x minus 2 is 2x minus 1 squared, right? That's what it was? 2x minus 1 squared. So, f looks like some higher terms. Then plus px squared plus qx plus some constant, let's call him r, for no reason other than to continue on with the alphabet. So this has got to be equal to f of x. We might need to worry about what these higher terms are. We might have to do my suggested plan of just pretend it's a cubic. I'm fairly certain we can find a cubic that'll do this. But if I plugged in, say, x equals 0, if x is 0, then we'd have f of 0 minus f of negative 2 is going to be 2 times 0 minus 1, so it'll be minus 1 squared, which is 1. But f of 0 is just r. And f of negative 2 is a whole bunch of stuff. But then this has got to be 1. And then maybe I could do something else like plug in f of 2. And then we'd get, if x was 2, then we'd get 2 minus 2, so we'd minus f of 0. 2 times 2 is 4, minus 1 is 3, so we get 3 squared is equal to 9. So f of 2 minus r is equal to 9. Yes, no, does that help us? I can't currently see anything that would help us here. I was hoping that I could get some numbers to just sort of work out for me. Is there any way I can get the same expression, but with by using different numbers? So what I'd like is maybe to have f of a and then f of b by plugging in different x values. So, b is a minus 2, but then plug in b and then have b be a minus, or a be b minus 2. No, that's not going to work. Yeah, this is an impossible equation. Okay, so I can't do any sort of symmetry thing, which sucks. What else could we maybe try? I'm leaning now towards it's got to be just find a cubic that does it, but maybe one more thing. Let's try x is 1/2. So this will be minus 3/2. Not particularly nice numbers here, but then we get 0 squared, so we get 0 here. No, I'm not liking this. I am not liking this one bit. I wonder if their solution has a cool, fancy way to do it, or if they just assume that f's got to be a cubic. Because we're not told. We're told it's a polynomial, so maybe there's just a really general way to do this. Then again, I'm pretty sure it's impossible for anything beyond a cubic to have the difference between two of them be a square. Pretty sure that's impossible. I'm willing to be proven wrong on that. But what are we to do? We want p plus q. So if maybe we had f of 1, we get p plus q, all the x's would go to 1s, certainly. That's not particularly helpful here. Well, I'll tell you what. If we had p plus q, and if x was 1, we would get a p plus a q plus r plus each of the coefficients for the higher terms. So if we took a look at f of 1, and then we subtract off f of 1 minus 1, so that'd be f of negative 1. Is that helpful in any meaningful way? So we get 2 times 1, which is 2, minus 1, so we get 1 squared there. And we've at least had that expression before, f of 0, which is just r, and f of minus 2 here. No, none of this is not working for me. So I'm going to go with my initial thought, which is a cubic should work for f of x. Maybe there's better stuff, but because the difference has a maximum power of 2, f of x should be max power of 3. Just like if we saw the difference between two of them was a power of 4, I would say it's reasonable to conclude f of x should be some sort of quintic, a power of 5 style polynomial. So I'm going to go with this, but in order for this to work, I do need to work out what f of x is and show that this relationship does work. Otherwise, I might be working with some f of x that doesn't satisfy their condition. And if we pick an f of x that does not satisfy f of x minus f of x minus 2 equals 2x minus 1 all squared, then we're not really working with an f that they're talking about, and so the p and the q that we get aren't going to help us. So we've got to find a cubic here that should do. So what does a cubic look like? ax cubed plus px squared. By the way, if you had the instinct that a cubic should work, go with it first, because I sort of had the instinct that there'd be a fancy solution. If there is, I can't see one, and look at the time I wasted. Okay, so this is what, in general, a cubic looks like. There's our P, there's our Q. We've inherited the same R, and usually the first thing is just an A. Okay. So now, if that's the case, maybe we can use equations like this to start solving for this sort of thing. Okay. So f of x minus f of x minus 2. Got to make sure the signs all work. So we're subtracting the whole thing, so it should be minus p x minus 2 squared minus q x minus 2 minus r. So that gets rid of those. Has got to be equal to 2x minus 1 squared. Okay. So the r's canceled out. Ax cubed plus px squared plus qx. So let's expand and simplify some of this. Minus ax cubed. Oh, geez, this is hard to do in your head. Plus 3 times 2. The heck with it. I'll just expand it out here. X cubed minus, and we'll have a plus, and then minus 8. So it'll be 3 times one of these 2's, x squared, and then plus 3 times 2 of these 2's times x. So it'll be minus 6ax squared minus 12ax plus 8 minus px squared. It'll be minus 4x, so it'll be plus 4px minus p times 4, so minus 4p. Should be an a there as well. Then minus qx plus 2q. And this has got to be equal to 4x squared minus 4x plus 1. Yeah, okay. So another thing to note, these ax cubes will go away. These px squared will go away. This qx will go away. So we're left with 6ax squared minus, or let's say plus 4p minus 12a x plus 8a minus 4p plus 2q. This has got to be equal to 4x squared minus 4x plus 1. So 6a has got to be equal to 4. A is going to be 2/3. That works fine. Now, negative 4 has got to be equal to 4p minus 12a. But now we know what a is, so this is 4p minus 24 over 3. So 8, bring the 8 over to the other side. 4 is equal to 4p. P is equal to 1. Okay, and now we can use the last equation to solve for q. So 1 is equal to 8a minus 4p plus 2q, right? I'm just going to go back and double check that. Don't want to make a mistake this late. Yeah. So we'll have 8 is 2/3. So this is 16 over 3. P was 1, so this is minus 4 plus 2q. So we'll get 5 minus 16/3 is equal to 2q. 15 minus 16 all over 3 is equal to 2q. So negative 1 divided by the 2, so negative 1 over 6 is equal to q. So there we have p, we have q, so p plus q is 1 minus 1 over 6, so that's 5/6. And this does work because we found the a, we found the p, we found the q, and the r has nothing to do with it. R can be whatever constant we want. So notice that was much faster if we just assumed it was a cubic rather than try and do something weird and fancy. And seriously, if you know a weird and fancy way, even if you go to their solution, look it up, and it's weird fancy, just let me know in the comments. Because I'd very much like to know if there's a quirky, fast way to do it, rather than just assuming f is a cubic. Fairly certain it's got to be a cubic. I don't have the math wherewithal right now to prove that, but I'm fairly certain it's got to be a cubic. So we'll just assume it's a cubic, and there was our answer, 5/6. What is that in terms of what we need to bubble in, if anything? It's B. There it is. So 24B, done based on an assumption that we can still quite easily confirm. If you want to, even write out your cubic with some R, doesn't really matter what R, and double check that this does satisfy the right properties. Otherwise, you might have solved for something improperly. But I think we're good. 5/6. And that does it. We've got one more question to go, so we're almost there at the end. So if you would love to, I would be honored if you would join me in my next video for question number 25, the last one on the 2000 Fermat. But that's all from me for now, so I will see you in the next video.